Hi, this is Mrs. Vrobel. This is part 5 of electrons and atoms. So we talked about light, what is light. We talked about the energy that's associated with certain wavelengths and frequencies of light. Um, we looked at the quantum numbers of electrons and the address that describes their location. Now we're going to do a couple more things. We're going to look at electron configuration, and we're also going to look at a drawing of the outer electrons within the atom. Okay, so before we get to that point, we need to talk about Heisenberg's uncertainty principle. And you may or may not have heard about this. Heisenberg was another physicist, and he found that it's impossible to determine the location and the velocity of an electron together. So what that means is when you are using an instrument to detect the location of an electron, you're affecting its velocity. And there's no way that you can know both measurements of that electron. Another principle that we need to talk about is the Aufbau principle, and it's actually the filling or the building principle of electrons. So notice that electrons, they always occupy the lowest energy or the lowest orbital. So when we look at electron configuration, this is going to be very important to understand. Okay, the next principle or rule that we have to follow for electrons, especially for electron configuration, is when you're looking at electrons, how they occupy orbitals, when they enter a suborbital that has more than one slot, you have to be careful. You need to fill one electron per slot before you double up. So always remember that if you have more than one slot for that suborbital, you have to put one electron in each slot before you pair up. And we'll talk about that more with electron configuration. This is the last piece that's really important with electron configuration. You can have no more than 2 electrons per orbital. So you can't put 3 or 4 within that one set of suborbitals. Okay, here we go. So with electron configuration, we're looking at how are the electrons placed within the atom. And we're going to look at the different energy levels that occur with that electron. And it'll make more sense when I show you the periodic table here. We're also going to draw, at the end of this video, we're going to draw the location of the outer electrons for the atom. And I don't know if you remember, about 2 videos ago, we looked at what a p orbital versus an s orbital and a d orbital. They all have certain probabilities of location within that drawing. So we're going to draw that at the end of this video. Okay, so here are electron configurations of hydrogen through neon. And here we have orbital diagram, and then we have electron configuration notation. I'm more concerned about this last part of the table. So just pay attention to the notations for the electron configuration, and we'll practice this at the end of the video. So for the first one, notice that we have 1s, and it has a little superscript at the top, this little 1. That tells you how many electrons are located within that orbital. And from the previous slides that we talked about, how many electrons can you fit in that s orbital? So you should say 2. Now, notice that we keep increasing the number of electrons as we keep moving down across the periodic table. Here we have boron. So notice with the building principle, the Aufbau principle, you're putting in 1 electron per orbital, and then when you fill in each orbital, you're going to start doubling up, okay? They want to occupy the lowest energies first before we move into the higher energy levels. And if you notice, there's an atomic number of 5 here. If you went across and added up all of these subscripts, it essentially would be 2 plus 2 equals, plus 1 equals 5. So the superscript should equal the same number as the atomic number. If it doesn't, something's wrong. Okay, so with carbon, we're looking at, once again, the single electron occupying each suborbital before you have doubling up. Notice that for nitrogen, we have 1s2, 2s2, and then we have 3 p orbitals, and we have 3 electrons, so each electron occupies one part of the suborbital, and we don't get doubling up until we reach oxygen. So notice that when you have a 4, that's when you get the pairing up of the first piece of, or first orientation of the p orbital. Okay, so here is a combination of a quantum mechanical drawing and a electron orbital diagram. So at the top here, and we'll draw this towards the end of the video here, this actually has the inner and outer electrons. So 1s would be considered the inner electrons, 2s and 2p would be considered the outer electrons. And I will never have you draw more than s and p, because D gets really complicated. I don't know if you remember it from the previous videos that you've watched. But notice that S is a sphere. It gets bigger as you increase the energy level. And then with P, you have the 3 orientations. So one is along the x-axis, one is along the y-axis, and then one is along the the z-axis. Okay, I'm just going to draw the electron configuration here to re-emphasize how we draw the electron configuration. So notice if I take these subscripts, 2 plus 2 plus 6, they should equal the atomic number. If they don't, you probably did something wrong. Okay, this electron configuration will help you with your homework. The nice thing about it is it's color-coded, and it actually shows you the different locations for the types of electrons. So this orange color is all s orbitals, and notice it's numbered from 1 through 7, okay? And they match the periods that are listed on the left-hand side here. When you get to the transition elements, that is not the case. Notice that the period does not match. So transition elements actually start with 3D. They don't start with 4D. Okay, please pay attention to that. That's very important. For the p orbitals, so notice that with the p orbitals, they do match the periods. So 2 and 3, 4, 5, and so on. This is helium, and helium is located over here. So remember, this electron is actually 1s2, just to remind you. With the homework, okay, this is where it gets a little tricky. You're going to notice that there's different types of periodic tables, and I know this is going to be confusing to some of you. Sometimes they carry the d electrons down to the f block, which is very confusing to students. So please make sure that you have 14 in a row. If you've got 15 in a row, they probably started off with the d electrons, okay? So you know you're dealing with 14 f electrons. You might want to count it just to make sure, okay? And notice that the energy level is 4 and 5. It's not 3 and 4, okay? All right, so let's talk about exceptions. Unfortunately, there are exceptions, and you're going to find a lot of these exceptions tend to be with the transition electrons. So in the d block of electrons, you want to have 5 total electrons, and it seems like it's energetic or energetically stable when you have exactly half full of the d electrons. So you're going to find the electrons, or I should say the elements that are near the 5th orbital, they're going to steal from the s orbital. And I will give you an example of that so you can be prepared for that. They also like to have full d electrons, so that once again they will steal an electron from the s orbital to complete the d orbital. Here are some examples. So here we have chromium. Chromium is very close to having its 5th electron, so you would think that it would be 4s2 3d4, but what happens is you lose an electron in the s orbital and it's given to the d orbital, and this actually is more energetically stable. That's why we see an electron configuration like this. Okay, so notice that the elements that are near the 5th d orbital tend to do this. Copper is another one. So copper, you would think the prediction would be 4s2 3d9, but what we actually see is 4s1 3d10. Okay, so you may notice electrons that are near that 10th d orbital will steal from the s orbital. Okay, so let's do some electron configurations here. And the first one that I have is chlorine. And notice I'm looking at 17 electrons. So that means all of the all the superscripts of the orbital should equal 17. Okay. Now I have a handy dandy periodic table that I want to show you. So this is like the one that I was showing you within the slide here. So I have 17 electrons, and what I could do a couple different ways, but I'll show you the first way. So here I have 1, 2 electrons. So I have 1s2, I have 2s2, I have 2p6. So right now that's 6 electrons plus 2 gives me 10. I need 7 more electrons. So I'm going to go to the 3s orbital, and I'm going to add 2 electrons. So that means I need 5 left. So I'm going to end up in the 3p section, and I want to count 1, 2, 3, 4, 5. Okay, so how do I draw it? Okay, so I'm going to start off 1s2, 2s2, 2p6, 3s2, and then 3p5. So when I add up all of these superscripts, so 5 plus 2 plus 6 plus 2 plus 2, it should equal 17. If it doesn't, I did something wrong. Okay, so now I want to do antimony 51. All right, 51. That's a lot, and I'm going to show you a shortcut. This is called noble gas notation. So once again, I'm going to go to my handy dandy periodic table here. Okay, so when I'm looking at 51 electrons, okay, I'll just give you a little hint here. I'm actually going to go to the last electron, and this is the noble gas that I'm going to use, okay? The noble gas over here is actually krypton, just to let you know. And I'm going to put it in brackets, and then I'm going to add 5s2. Notice I'm going into the d electrons, so I want to write 4d10, and then I'm left with 3 electrons. So 1, 2, 3. I'm going to end up with 5p3. Oops, sorry about that. Oh, went too far. Okay. All right, so for antimony, this is, like I said, the noble gas notation. So I'm going to put krypton in parentheses. So I'm assuming this has the same electron configuration as krypton. And then I'm going to write 5s2, 4d10, so notice it's not numerically in order, and then 5p3. Okay, and if I added up all these subscripts plus the atomic number of krypton, I should equal 51. Okay, here I go. Now this is silver, and I'll just tell you ahead of time, this is an exception to the rule. Okay, so don't be surprised if we have to steal an electron from the s orbital. Okay, this actually has the same noble gas notation as krypton. Okay, and then after krypton, we have 5s2, and then 4d9. Okay. Well, guess what? You're going to steal a 1 from this s orbital, and you're going to make this 4d10. Okay, because it wants to complete. You know, I'm just going to scratch this out and draw a 10 next to it. It wants to complete that 10th orbital, okay? This is your homework, and I'll just let you know there are F electrons, and I would look for the noble gas that is the row before this, okay? So the last element before this row, I would pay attention to that, okay? All right. Let's go to the next one. Here is quantum mechanical drawings, okay? Now, before you do this, what I would do is I would write out the noble gas, I would write out the, well, you can use noble gas notation. I would write out the electron configuration for it. Okay, so for sulfur, the closest noble gas in the row before is neon. And we have 3s2, 3p4. Okay. Now, I'm not going to have you draw the inner electrons. I just want you to draw the outer ones. Okay. So what I'm going to do is I'm going to have a big sphere, and I usually draw it right outside the crosses because it's easier that way. And then I have 3p4, and I don't know if you remember, but there are 3 slots for the p electrons. So I'm going to have 3 lobes, and I'm going to do sort of like big figure 8s around each orientation. Okay, so this represents the 3 different orientations within the p electrons. Now what I'm going to do is I'm going to draw the electrons for the s orbital, and I'm just going to include them in the sphere. So you have a spin up and a spin down. Now I have 4 electrons. So I'm going to put 1 electron in each type of orientation. Okay. Now notice I only have 1 more electron, and I'm going to just draw it in the opposite direction to symbolize the fact that it is spin down. So I only have 4 electrons in the p orbital for that, and that's how you would draw a quantum mechanical structure. Now for neon, neon is helium. Okay, and then its electron configuration is 2s2, 2p3. So I'm not going to draw the electron structure for that. I'm just going to do 2s and 2p. So once again, I'm going to draw the s orbital, and then I'm going to draw the p orbital. So I'm just doing little figure 8s around each orientation. Okay, so once again, I'm going to draw the pair of electrons in the s orbital, and then for the p orbital, I only have 3, so I'm only going to put 3 arrows and 1 in each orientation. Okay, so make sure you do that electron configuration and study your quantum mechanical structures.